I'm going to be talking a little bit about the enzyme catalysis research and project for biodiesel that has been done at Piedmont and some of the other commercial applications of the use of enzymes in the biodiesel industry. If you were at the class yesterday, we had a day-long workshop where we covered some of the enzymatic applications for biodiesel, and we got to do some hands-on trials of using the enzymes. So this is going to be kind of a short and condensed version of that class. So those who are sitting here and were in the class yesterday, you may be called on for some answers. So I'm going to speak a little bit from our experiences, my experiences at Piedmont a number of years ago. I was the PI on a Department of Energy research grant investigating the use of enzymes as a catalyst for biodiesel. And some of the reasons why we were looking at enzymes, one is on the sustainability front and one was kind of on our water footprint. And I kind of looked to Simon Sinek as an inspiration, as, you know, people don't buy what you do, they buy why you do it. And if anyone who has been around Piedmont would say that is really speaks to why people are driven to biodiesel around Piedmont and its findings. And so this is just a picture of the facility. You guys will get a tour coming up in an hour or so. So here's kind of the outline of what I'm going to cover today. Why would you use an enzymatic approach to biodiesel over chemical catalysis? What are the sustainability implications there? What enzymes are available commercially today? Which enzymes is best for transesterification, esterification? How those enzymes might be reused more than one time? And a little bit on the economics of the enzymatic biodiesel front as well at the end. So quick definitions. Most everybody here, if you've been in biodiesel, you know most of these terms. Triglycerides, TAG or TG, diglycerides, DAG, DG, free fatty acids, I'll probably say FFA or free fatty acids multiple times. FAME and FAE, we've made biodiesel from both methyl esters and ethyl esters, biodiesel using ethanol. Primarily most of what we see here in the United States is biodiesel that's made using methanol. There's a number of different types of enzymes, immobilized enzymes and liquid enzymes. We looked at both types of enzymes. The immobilized enzymes are enzymes that are put onto a plastic support, different supports, sometimes silica supports. I've got a sample here, so this is a sample of the immobilized Cal-B or Candida antarcticus lactase B. If anybody's ever seen it, I'll just pass that around. And then free enzymes, liquid enzymes, those are actually seeing a little bit more light of day in the commercial applications. I think the Novozymes formulation is Claritrans. That was a variant off of the TL, Thermomyces lanuginosa. And so we've got a sample of that. And we made many batches using the Claritrans in our workshop yesterday, both looking at corn oil. We used a crude 12% free fatty acid corn oil and a 5% free fatty acid yellow grease with different reactions. And so if anybody wants to go and look at that setup in the laboratory after the class, happy to go show you guys since we didn't do the class right there. So these are the kind of key advantages to the use of enzymes for biodiesel. Piedmont specifically was looking at the use of enzymes to reduce wastewater effluent. So the facility that's built here in Pittsboro, our wastewater treatment facility for the town is limited in its actual wastewater capacity. We do have an Piedmont has an industrial wastewater permit, but the amount of water that could be discharged was very low. And so that was why we started to look at how are the different ways that we could reduce our water footprint? And one of those ways is, okay, well, why do we have a water footprint? We have a water footprint because when you traditionally make biodiesel using hydroxide catalyst, you create soap. What do you have to do with that soap? You have to wash it out. And so therefore you end up having a soapy wash water. If you don't have soap in your reaction, then you don't have to wash it out. And how do you do that? Well, find a catalyst that doesn't make soap. Enzymes are catalysts that could not, that do not make soap. So that was one of the reasons, a big attraction to looking at that catalyst. The other piece is when you don't make those soaps, you don't also have a contaminated glycerin. So the glycerol that typically comes off biodiesel process can be 50 to 65% purity. It has a significant amount of residual soaps and salts. We've got a couple of samples here. You guys who have been making lots of biodiesel for many years know that there's a big difference between pure glycerin and the crude glycerin. So I've got two samples here. One is a yellow grease that used potassium hydroxide in its process, and another one that used only enzymes in the process. And you can see that the glycerol coloring just and the purity are quite different. So enzymes have the capability of both doing esterification and transesterification and hydrolysis, and we'll go into that a little bit more. Overall, you know, there are several benefits, but there are also some things that you need to be aware of. It's a much different processing and maybe somewhat counterintuitive to how we typically produce biodiesel. So again, I mentioned sustainability as one of the reasons why we were attracted to the use of enzymes, because one thing that has always been at the forefront for Piedmont Biofuels is trying to not only make biodiesel, because biodiesel in itself is inherently sustainable, but is there a way to have a zero waste process or a very high, high energy balance and overall high sustainability factors. So one of the things that we looked at is there was a life cycle analysis done between enzymatic and chemical catalysis for biodiesel back in 2007. And that really showed that there is a benefit for using enzymes over chemicals. And if you're just looking at the comparison of not using any kind of sulfuric acid in your process, the two key points here were the marine aquatic ecotoxicity and the terrestrial ecotoxicity, and the freshwater ecotoxicity were all pretty significantly reduced when you pull that mineral acid out of the life cycle analysis. So there are and have been some hurdles to the use of enzymes in biodiesel. So we'll first hit with very slow reaction times. So most of the early research over from the mid-80s to mid-90s, you're looking at enzyme reactions that were at 24, 48, or 72 hours. We typically, in biodiesel production, are comfortable with 1, 2, 3, maybe 4-hour processing times at most. When you go to me and say, hey, don't you want to tie up a reactor for 24 or 48 hours? And that sounds like not that much fun. So people haven't been commercially looking at enzymes because of the very slow reaction times. Now those reaction times have improved significantly over the last, I would say, 5 or 6 years of commercial implementation. So that was one of the things that we felt like we helped improve for the industry. And then the other thing is meeting the actual ASTM specifications or the European specifications. So things that were investigated in the literature. So there were many enzymes that were looked at and trying to use in processing for biodiesel, but none of those academic researchers actually ever tested the material, the ester material that came out of their small, tiny little vias to an ASTM specification. So That's the little flag that we put on the moon, that we were the first ones that actually ever tested the biodiesel to an ASTM specification and said, yes, we were able to use enzymes in the entire process and able to meet the ASTM specifications. Next hurdle, and this still continues to be, I think, a hurdle for the industry, is a high catalyst cost. So when we look at the cost of sodium hydroxide, potassium hydroxide, or sulfuric acid, those are, you're talking pennies on the pound, and enzymes are an investment. But you can think of it not only as an investment in a one and done type of catalyst, but an investment in something that can be reused several times, and an investment in yield. And so we can go into, the need for some of the enzymes must be reused multiple times more than, mobilized enzymes typically cost more. And so if you can reuse those multiple times, upwards of like 60 to 100 times, then you have an economic payback. On the liquid enzymes, you can actually see only, if you can reuse those at least 5 times. We've seen good reuse up to 10 times in some of the pilot trials that we did at Piedmont. So there is the capability of reusing the enzymes. Also, the enzymes a number of years ago, they had never been tested on low quality or real world feedstocks. So those are some of the things that we push forward in our Department of Energy research, testing enzymes on fish oil, on brown grease, on yellow grease, on corn oil that came from distillers grains ethanol facilities. And then the other 2 hurdles that still exist, because these are just a function of the lipase or a function of the enzyme themselves, is they can be deactivated by either alcohol or glycerol. And so we experience some of that. So one thing you need to know is you need to be when you're dosing your enzymes or dosing your reactor with methanol, you can't do it all at once. You have to carefully kind of couch the process and make sure you do not overdose the alcohol in reaction with the enzyme, because it can deactivate it. We also experience glycerol deactivation or glycerol agglomeration, in which the immobilized enzyme could be coated with glycerol, and it kind of suffocates it or prevents the active sites, the place where the catalytic activity happens in the enzyme, from being accessed from the triglycerides or the free fatty acids. Any questions? So just a little bit of a background on some of the earlier work. Pay homage to one of my mentors at the USDA, Mike Haas, who's been very active in the biodiesel industry. He was a mentor, an advisor on our Department of Energy research. He worked with Tom Foglia, also at USDA, and Martin Mittelbach from the University of Graz. They did much of the earlier work on enzymatic application. There wasn't significant production. This was all lab and research scale. Then in the late 90s, early 2000s, you saw the first actual large-scale production plant in China using terpbutanol and immobilized enzymes at that time. And then after 2008, 2009, that's when Piedmont and Novozymes teamed up and were working together. There are other researchers out there that have been investigating different enzymes and applications. Korea, Israel, the folks in Trans Biodiesel have also. And now we have seen an actual implementation here in the United States. There are a number of commercial producers, like the folks at Blue Sun Biodiesel who have been implementing the liquid enzyme process. So why enzymes and why now? Why didn't they come around 10 years ago or 5 years ago? I think the biggest thing is the biodiesel industry has grown. It's much more mature now. And there has been more experience with a wide variety of feedstocks. And there's an interest to look at lower quality feedstocks and an increased fuel quality. kind of a range of factors that come across all at the same time. And you put those together with the fact that you have stronger developments and more robust enzymes, and having those robust enzymes at an economic price that biodiesel producers can afford. So as I mentioned before, reusability from a biodiesel producer's perspective, being able to reuse the enzymes more than once really can impact the commercial viability and the economic piece of the process. The things that do absolutely deactivate enzymes, don't cook them, don't get them too hot. They really like to be somewhere, under 50 degrees C, under 120. Don't overdose it with methanol, so don't accidentally open that methanol valve and give it a methanol bath, because you'll be crying later when you look at your balance sheet. Immobilized enzymes, the ones that are immobilized on the support structure, alcohol out of phase and glycerol out of phase can negatively impact that. If you have too high of a shear, so some of the enzymes, if they get caught into certain types of pumps, or that basically the enzyme can kind of be knocked off the support, and therefore you have some deactivation there. Polar contaminants and mineral acids, so things like gums and waxes and any type of acid that you may see in acid esterification or neutralization, acid esterification, or that type of process may have a negative impact on the enzyme activity. So those are the key things that can key things you need to watch out for. Hey, Bob. Just one, I'll mention some of the researchers out of Japan, Watanabe and Shimada. They really kind of pushed or helped optimize one of the things that we now see implemented in the commercial application of the use of enzymes in biodiesel, and that's the stepwise addition of alcohol to avoid deactivation. So one of the key pieces is basically we just squirt a little bit of methanol in over a long time period. And that specifically, you can do that both with the immobilized enzymes or the liquid enzymes, but if you're just a little bit at a time, can keep the reaction going and not deactivate the enzyme. So they have a number of papers out. I just kind of pulled one example of how they were able to get really high conversion. Now look, it was very long conversion times, but just small amounts of methanol in that stepwise addition. This is older work that was done by Enzymes. At this time, in 2009, they were still using a very large amount of methanol at the time. They did see some deactivation. And they were a little bit higher temperature conditions, but they were primarily looking at palm fatty acid distillate, and they were blending the palm fatty acid distillate with biodiesel to try and get good conversion. Now, if you'll see, your reaction times were much lower than what you've got over here. So we're looking at 80 hours here. This is a much different reaction application here. This is more on the esterification piece. And so much quicker reactions. Was there a question? Just somebody's food digesting back there. This is a picture of, I think, the first version of Piedmont's enzymatic pilot reactor. So we, at Piedmont, we started looking at enzymes in 2008, 2009. The primary focus was on esterification. We moved from the lab to the pilot in 2010. We had funding from the Biofuel Center of North Carolina. In 2011, 2012, we moved from the pilot to commercial integration. And again, we were really the key there is that we're able to demonstrate that the use of enzymes can meet a full ASTM specification. So these are two of the enzymes that we were looking at. So the Candida antarcticus lipase B, CAL-B. The Novozymes version out of that is Novozymes 435. And then the TL, at first we were looking at the immobilized version of TL, Thermomyces leguminosa. And you can see that there are some variations in the reaction between the use of water and the use of low water conditions. So CAL-B can esterify very quickly, and when I mean very quickly, we're talking 30, 60, 90 minutes in low water conditions. It can also esterify pretty quick in some water conditions, and I mean we're talking about 1% or less. But if you have even higher than 1% water and you're using the TL enzyme, whether it's immobilized or in a liquid form, it can esterify pretty quickly. So you can see that both of them will do both, but they can be optimized to different reactants. So just a picture of the different enzymes that you're looking at, the liquid formulation, the Calera Trans on the left, and then the one on the right-hand side is the immobilized CAL-B or Calera Ultra. So we had originally looked at this Thermomyces immobilized enzyme. We were looking at a variation of 0.5% to 5%, still very long reaction times, but lower amounts of methanol than you typically see in our traditional process of like somewhere around 20%. But the big problem that happened there is that we saw this glycerol agglomeration. So the enzyme, you basically, your biodiesel, and then you'd have your solid phase of your enzyme in there, and it would sit on top of the glycerol. But because it was so close to the glycerol, and that glycerol would basically suffocate the immobilized enzyme, and it would be something difficult to process and wash. You can wash it off, but it was just kind of a little bit of a processing nightmare. So that's when we kind of went back to Novozymes and said, hey, let's look at a different, is there something else that we can do here? And Novozymes kind of went back and reformulated a different variant of the enzyme into what we see now, the Calera Trans liquid form. And so that's when we did a number of small-scale batches, and then we ran a pilot batch here at the community college, and I'll show you some pictures of one of the reactors that we used here at the community college. And then we scaled that up to 2,800 gallon reactor at Piedmont using one of the just standard reactors. Really no bells and whistles on it. It was just a conical tank, pump mixing. I think it's got an inductor in there. It's no overhead propeller, but you can use that. So we looked at a variation between 0.5% and 2% by weight. The reaction time was improved from 10 hours to 33 hours down to 4 to 24. Novozymes will say 35C is kind of the optimal. We were able to reuse the enzymes up to 10 times, but in an economic way, if you can at least get 5 reuses out of there, then you've gotten your money out of the enzyme. You basically, the samples here, I've got a couple of samples of similar batches to what we ran on the large commercial scale. And this is the very, very same process, the biofame process, that has been being implemented at a couple of different commercial locations today. So this is a yellow grease sample, and you use a small amount of water. This I think was 2 or 3% water, and this is a yellow grease sample. And what you see is there's kind of a hazy little emulsion phase in the middle, and then the bottom phase is the glycerol, and then the top phase is your biodiesel. This is a very similar sample where you have the soybean oil, and the emulsion phase is the enzyme that you're going to try and reuse, and then the glycerol is at the bottom.
How are you recovering your enzyme? You cut the layer very carefully?
It's a very careful phase separation. So We did some research, basically doing side-by-side comparison of ultrafiltration applications, of doing a phase separation, basically pulling the glycerol, thank you, Ron, pulling the kind of emulsion layer and the glycerol phase and pushing that somewhere else. And you could wrap it back into the reactor. We also looked at running that material through an ultrafiltration membrane and then pushing it back. The thing you have to be careful of is if you're familiar with biodiesel processing, a significant amount of your methanol or excess methanol from the reaction is going to hang out in that glycerol phase. And so you got to be careful about not building up too much methanol and having it deactivate your enzyme after you basically save it each time. So.
I've never thought of a co-solvent or putting something in there to enhance that separation so it's less of an emulsion, more clear cut.
You could. I mean, personally, I'm kind of the school of thought of the KISS method, keep it simple, stupid. So co-solvents aren't as simple, especially when you have emulsions involved. So essentially what you're going to get after this reaction is you have a biodiesel that's about 97% converted, so about 97% FAME, lucky 98% FAME, but you have some residual free fatty acids in there. It's going to be about 2 or 3% free fatty acids, and the reason why is because the liquid enzyme, it's a liquid, it has water in there. It also has glycerol, so the liquid formulation has water and glycerol in there. If you put water in with your triglycerides, you're going to have hydrolysis and you're going to create some free fatty acids. So some remaining free fatty acids will never leave that reaction because you're using the use of a liquid enzyme. You're always going to have some water in there. But one thing that is kind of neat is that you could reuse wet methanol and you don't always have to dry your feedstock. So if you put a lot of energy into drying your waste vegetable oil, or you're able to purchase cheaper wet methanol, those might be some different applications for using the liquid enzyme. How do you deal with this residual free fatty acid? We will get to that in the coming slides. So this is commercially, I don't think it's formally launched yet, but the name of this process is called the biofame process. And one way that you can actually remove those free fatty acids is by caustic stripping or caustic wash. It's not my preferred way, but it is being commercially used today. And the reason why I don't think it's the ideal solution is because we've had experience with emulsions and trying to crack emulsions, and so this is a sample of biodiesel. I took some biodiesel that had gone through the liquid enzyme process and just did a dilute sodium hydroxide stripping solution. And they say to agitate it at like 60 degrees C for a certain time period. It says right here, 2% dilute sodium hydroxide caustic treatment at 60 degrees C. What are you doing? You're essentially making soap stock, and you have to acidulate that soap stock and try and recover the free fatty acids that you just made soap out of. I don't know, personally wouldn't like to have a whole big tank of that. But so this is kind of what the caustic wash looks like. One of the ways that was investigated at Piedmont is using kind of a custom reactor that used the immobilized enzyme. It's the more expensive enzyme, but you can reuse it several times because you're basically feeding it a very clean biodiesel. And personally, I like the phase separation on this guy better. This is just kind of for the liquid enzyme process. Remember I mentioned that you are seeing some hydrolysis. So what happens is, say if you start with somewhere around a 10% free fatty acid feedstock within the first couple of hours, depending on how much water that you use in the process. And we used a range of anywhere from really 2% to 20%. You see a pretty strong increase in your free fatty acids. So you have a strong hydrolysis reaction that's happening first, and then the enzyme kind of like switches gears and says, okay, I'm not going to hydrolyze anymore, because there's more FFA, and now I want to esterify that. And so they start esterifying, and then you basically come out with somewhere close to 97, 98% free fatty acids by the end of that 24-hour reaction. So this is a couple of pictures of some trials that we did here at the community college with the help of, Bob, were you in Ghana already?
No, I was not. I was here.
Okay, so
I thought you were putting a different temperature control on.
Yes, exactly. So what we did is the BioPro is not tuned well for not cooking the enzymes, so we had to do something so that we wouldn't get the reactor too hot, and we changed out the temperature controller, and then we also had to figure out a way to just slightly dose the methanol. We've actually I've been working with some guys, some of the older design build guys, and we've kind of come up with a more sophisticated way to do this in a more automated way of dosing and temperature control that we'd like to offer to any folks who are using BioPros. And we've been working with the guys also at Springboard Biodiesel to kind of be able to offer that. So this was some of our early trials where we were basically using the liquid enzymes, doing a small dosage, controlling the temperature under 100 degrees. And so these were just kind of some of the reaction conditions. I think we were at 40 C, it's a 42-gallon reaction. We used both 1% and 2% enzyme. At that time, the aqueous phase was a little bit more, so we were using more of a 20% water glycerol solution. Novozymes has kind of done some of their own optimization to chase that aqueous solution down to a 3% water. Very similar methanol dosing still. We would basically dose the reactor with 25% initially of the methanol that's required, and then over time we would meter in the remaining methanol over the process, over a 5 or 6 hour process. Those are things that can kind of be optimized or tweaked. Different producers may look at different metering times of the methanol. And so these were the results on the BioPro. So we're able to get to, I think we started with a 12% free fatty acid yellow grease, and over 24-hour reaction, we got down to like it was 2.5% FFA, and the bound glycerin was basically in spec on the bound glycerin front, and then we just had 2.5% FFA to deal with. We also did the same process, and we reported this at the National Biodiesel Conference a couple of years ago, in which we scaled up the same thing that we did on the BioPro. And actually, we got better results. We were really surprised that we got better results on the free fatty acid. But our methanol dosing was not very sophisticated at the time. It required like me and Paul and Ray being at the edge of a tote, manually valving in the methanol. So now we have, on the pilot scale, the pilot unit that we have a little bit of a better way to dose in the methanol. So there really is just a balancing act between, the water, the methanol, and the activity of the enzyme. If you give it too much methanol, it's going to deactivate the enzyme. If you give too little methanol, you're going to have a slower reaction. Too much water, you're going to have too much hydrolysis. Too little water, you also may lose some activity on the enzyme. So we did kind of a second phase of trials with the BioPro where we were looking at this manual gravity separation, which we really Paul determined. He called it the selective aqueous phase reduction. It's a very scientific term. And what we were using some technology from Smart Flow Technologies, their tangential flow filtration unit, to do some cleanup of that aqueous phase. So this is just similar to the sample that I sent around. You've got the biodiesel on top, you've got the emulsion enzyme layer on the bottom, and you've got your aqueous phase of that has glycerol and methanol on the water. And basically we would do kind of side-by-side comparison of, can you just do a gravity separation, or would it be good to actually run this aqueous phase through this ultrafiltration unit? Both technologies do work. It's a matter of how much money you would want to spend on that type of technology. And at the time for Piedmont, it was cost prohibitive. So a little bit about the faster process. This is the way that we would esterify or polish the free fatty acids after the biofame process. And that's, we do it in either 1 to 3 stages, where you can basically esterify. It works best with an immobilized Cal-B. You can do it with a liquid Cal-B, but because there's a liquid formulation, it's not as fast. So it's hard to call it the faster process when you're using liquid Cal-B because it's not that fast. So this can replace traditional sulfuric acid esterification. It's again, another low temperature process. I think the unique part of it is that it really maintains the water balance in the esterification process. So you can use the faster process as a pre-treatment, and that's the way it's designed and it was implemented over at Piedmont. If you have really, really high free fatty acid feedstocks, so like something like a palm fatty acid distillate, you can completely convert that palm fatty acid distillate in 90 minutes using this process. And then I think it's an economical way to address the free fatty acid in the biofame process because you're only esterifying 2 to 3% free fatty acids. So we've proved it out on a number of multiple feedstocks: brown grease, palm fatty acid distillate, yellow grease, corn oil. Typically, you esterify pretty quickly within 30 minutes, and it's usually into the acid value specification by 90 minutes. So this is the two, kind of do it a 2-step enzyme-based process, and then you can, what we proved out both on the BioPro and the commercial scale, using those two, we were able to get the fuel into ASTM specification using those 2 steps. And so that's just a copy of the ASTM spec that we did on I think that was in 2012. One of the nice things about using the enzymatic process is that you do have a much cleaner glycerol. So these are samples from Piedmont's chemical-based process. You got about 55% glycerol content, high moisture, a lot of ash, probably some material, organic non-glycerol or emulsified biodiesel in there, and some residual methanol. If you look on the enzymatic side, it's pretty high purity glycerol. If you remove that moisture and methanol, you can really upgrade it beyond just a technical grade glycerol. So you're looking at a variation between 5 cents per pound down to up to like 40 or 50 cents a pound. Just some specs on glycerol co-product values there. So some of the reuse data looking at the longevity of the enzyme. Piedmont's live trial data showed that on the immobilized Cal-B, we could get to 15 cents per gallon. That's on the pre-treat side. I think on the polishing side, it would be much cheaper than that 15 cents per gallon. Also, since this live trial data, Enzymes has done some more work on the immobilized enzymes, and hopefully we'll see some of that work in the commercial sphere in the next year or so. So we have both live trial or enzyme reuse data on the liquid enzymes and enzyme reuse data on the immobilized enzymes. And we did side by side, we actually surveyed the biodiesel industry, got a number of different yellow grease samples and did live trial data on the yellow grease samples from all over, from biodiesel producers throughout the country on esterification with Cal-B. And then we also did some of that, mostly with the feedstocks that came out of Piedmont, and we found that, we were seeing somewhere, economic viability within 5 or 6 batches. So just a couple pictures of some of the commercial installations that are out there. So this was the implementation of the faster process at Piedmont. And then Blue Sun Biodiesel in St. Joseph, Missouri. They're using a part of the biofame process, and they're very large scale. So you're looking at 3 80,000 gallon reactors. They have their own proprietary mixing system. Everything is completely controlled in terms of automation. So, and this is some of the work that they reported at the American Oil Chemists meeting in the past year. Trans Biodiesel, that's Sobi Bashir out of Israel. He's been involved in developing not only the enzyme process, but his own version, his own enzymes himself. And they have their own intellectual property around the way they immobilize that enzyme. So this is just a couple of slides. So they typically are able to, they do kind of a dual phases where they're doing some kind of trans-esterification, then esterification, and then some post-treatment. But you'll see their post-treatment, they still have some residual free fatty acid, and they treat it with a resin and a caustic wash. They have recently, in the last year or so, installed a process in Korea, commercial scale process of 96 tons per day. There's another company in Florida that has implemented the use of the liquid enzyme process. From my knowledge, they're still using the caustic wash, but are looking at other ways to deal with the free fatty acids after the use of the liquid enzyme. They do acknowledge that they have some yield loss with the use of the caustic wash, and acidulating that free fatty and acidulating that caustic wash material and recovering the FFA is difficult. They've looked at a couple of different other ways instead of the caustic wash. One of the ones they recently reported is the use of different catalytic resins, so different resins that may do actual acid esterification or water absorption. And I believe that they also reported that they are able to use some brown grease and use cooking oil, but I don't think that they're using 100% brown grease and able to convert that 100% brown grease. And then there's also the limiting factor of the sulfur levels. So just to summarize, the enzyme catalyst biodiesel production is commercially viable. People are using it today and making fuel that meets the specifications. It does eliminate the needs for acid or caustic catalyst if you're using a two-stage process. You can use a wide variety of feedstocks. The enzymes are reusable, and they do have competitive both processing costs and capital costs to the producer. Any questions? Go ahead first.
Yeah, sure. Can you talk about ethanol?
Ethanol.
Yeah, you talked about it in the first slide, and you sort of said, we don't do that much here. Something about Europe.
Well, really, when we were doing our research collaboration with Novozymes, when Piedmont was, they had a strong interest in making ethyl esters for, I think, the South American market, for the Brazilian market. So we did a number of trials using ethanol just primarily for that interest.
Okay.
So it works, but you know, it wasn't our driving force because we were always on the methanol side.
Sure. I mean, some of us have an interest in not using methanol as our feedstock to make fuel, right? So I don't know if this is advancing us in that direction in any way. Is this a positive step?
I mean, it's a possibility. So I'm happy to share some of our ethanol-based reaction conditions if you're interested.
Sure.
So. Matt in the back.
Yeah, just curious about the FFA problem. Has anybody considered distilling out of the ester, the ethane, for the FFAs? Is there a wide enough temperature distillation difference where you could separate out that way?
Just do it kind of like you do basically a steam stripping. You can have, because there's
I'm saying actually distilling either your esters or your FFAs straight out and getting a pure stream of each.
I know that there are biodiesel producers that do that, but they do it on the feedstock side, not on the biodiesel side. So.
Yeah, no, I know that happens. That's why I was thinking, is it possible on the biodiesel? I know that people are doing it on the feedstock side.
I haven't heard of it on the biodiesel side.
That's why I was thinking
Yes.
With the liquid and the immobilizer, are they both the same temperatures issues, like at 122 degrees, or have you tried one at a higher temp?
I think that on the CalB we went up to 60, but really on longevity side things, if you can keep it in for CalB in the 45 or lower, that's ideal. They do say, Novozymes will say that 35 is ideal for Clara trans. We did push that, but I think, you know, again, it's a balance between how many times do you want to reuse it and your deactivation and the temperature use. So, you know, I think that we were talking a little bit towards the end of the workshop yesterday. If you did want to have a much quicker reaction and you didn't really care about reusing the enzyme, could you use a lower dosage amount and a higher temperature? It's possible. Yes.
Have you tried like a continuous flow, like in a column, instead of essentially an emulsion with immobilized enzyme, the matrix, your oil, glycerol, methanol? I mean, the way that you
on a esterification with the liquid enzyme or the mobilized enzyme?
No, immobilized enzyme. So like in a column that's being flowed over continuously, let's say, instead of, is that how you did it, or?
No, I have tried that. That's not how it is working the best today. The thing is, when you are esterifying, you're always creating water, and how do you get that water out of the process? So in the column, you also have the potential for any contaminants clogging or plugging. So the column hasn't been, I think, the most ideal setup. People have looked at it significantly in the lab. Ron, question?
Can you talk about the reactivity of the enzymes after each reuse? Does that does the reactivity go down? So is it as effective after each reuse?
No. So you use it, it's a little bit deactivated after the first time. You reuse it again, it's a little bit deactivated. No, so there is the way you can play with, if you're gonna put it back in and maybe on the third or fourth time, maybe you put a little bit new enzyme in there to kind of keep the old guys happy. And I know that, where's Professor, I don't know, he might have just walked out. We were discussing that in the workshop where they were kind of doing, maybe not a lead lag situation. Professor Rowland, we were talking about reactivating the enzyme and using older enzyme for the first batch. There was a question. You want to re-ask your question, Ron?
I'm just curious to know when you reuse the enzymes over and over again, does the reactivity of the enzyme
I've done this after 4 times. We still have the same activity. You don't have to add new enzymes. If you start to use it the 5th time, you add a little bit of more enzyme again.
Okay,
Yeah, but 4 times is possible. Yeah.
thanks.
Maybe the enzyme will become better and better also by enzyme, so maybe we can do it 10 times.
More
But
than that.
the separation for your enzyme from the glycerol, you have to control it very carefully, okay? Don't use EAT or things like this or too much glycerol inside. Yeah, that's not that easy.
Okay,
Yeah.
thank you.
Question?
Just ask Alice, but I was wondering if times vary based on feedstocks, if it takes longer.
No, it's, we were, in the lab, we were processing a 5% free fatty acid yellow grease and a 12% corn oil, and it's the same processing time.
And as far as cost, so you said, if you can use it like 5 times, it's the same as like traditional using like sodium methylate or?
Yeah, we did
Does that
basically,
include selling the glycerin at a pure grade?
it is at selling the glycerin at a higher grade. But it didn't include RINs when we did the cost analysis. So, policy issues, tax incentive issues out of the way, just catalyst to catalyst. On 5 times reuse, you could do it. Yes.
You mentioned that when you scaled up from the BioPro to the larger processor that you had much better results. Do you know why?
I think that there was, it had to do with some of the methanol addition, and the timing of it was not
The
as
lack
sophisticated.
of accurate
Yeah.
metering
Yeah.
in the smaller scale.
And I don't know exactly why we got down to below that 1.5. I'd have to go back and look at the results, but it wasn't significant variance.
In other words, if you repeated the same trials with the BioPro and with the larger processor, you would still come out with the same difference.
It's, it's been repeated enough that it's a right around that 2%. Yeah. So I think it's going to be, I think Novozymes has done some work and been able to kind of chase it a little bit under that 2%, but on average, I would report 2%.
Oh.
Yeah.
I'm still after this commercially available question.
Yes.
Is that something you can discuss here with us, or is that something? We have
Well, I don't sell the enzymes, but I'm happy to, one of the things that I'm doing and through my work at Mark IV or through other entities is assisting others that might want to implement the technology. So Novozymes and Trans Biodiesel are the primary ones that are selling enzymes. So those are the people to talk to buy the actual enzymes.
Well, I assume there's considerably more involved than just buying the enzymes.
Yes. Happy to talk to you further afterwards.
Okay.
Yes. Any other questions? Jason, come on. No questions? Something from the back?
No, I thought it was fantastic.
All right.
I have one more.
Yes.
Did the cost analysis take into consideration the decrease in energy needed to heat up and?
Actually, no, it didn't.
And I assume there is a
Yes, there is.
measurable decrease in the energy needed to get the reaction.
Now, we did that. I did some cost analysis and comparing the liquid enzyme to sodium and potassium hydroxide. It did not include the heat value, but I know that Novozymes has done that cost analysis. When we did the cost analysis of comparing sulfuric acid to a mobilized enzyme, we absolutely did count the heat factor and the methanol, rectification costs. So that's the big cost advantage if you're going to just use immobilized enzymes compared to sulfuric acid, is that you have a lower amount of methanol and you don't have to rectify that acidic methanol. Well, if there's not any other questions, do we have time to go show them in the lab, the little setup? Or
You do. So what's happening next is, well, first of all, thank you.